Hi. So today the topic we're going to discuss is transistors, and to make it more precise, we're going to talk about bipolar junction transistors, in short, BJTs. In the last video, I talked about why we need power electronics, and we were talking about potentiometers and linear electronics that we use, but there's a lot of power losses. So that's where the transistors or diodes and everything such that of power electronics comes into play. So today we talk just a general description and a precise and accurate way of knowing what transistors are. Like I've said this before, but the videos that I do, they're for me to come and recap, and I want others to get some knowledge about power electronics or electrical engineering in short. Um, it would be great if someone tells me if I'm wrong or like corrects me in the comment section, or provide me with more information or articles. Um, anyways, moving ahead. Today we will talk about BJTs. So bipolar junction transistor, the name comes being bipolar. It means that let's just draw the general structure. So this is basically what, just mind my drawing, I'm not really good at this. But this is an NPN. We're basically going to talk more about NPN, but there's one more which is PNP. But right now we're going to consider it NPN. So an NPN, we have basically emitter over here. This is the base and this is the collector. This N region is highly doped with electrons. This P region is highly doped with holes. And this N region over here, it's moderately doped with electrons. So this is a general way of knowing what a BJT looks like. So why bipolar? This is one pole, this is the other, so two junctions, so BJT. Now, before we get into more about this, we should know the general. Okay, so NPN's basic structure kind of looks like a diode, like this. This is one diode, D1, D2. So this is how it basically looks like. So we can get more information on this, but let me just remove all of this. So yes. So before we get into this, let's just know a little bit about diodes. So diodes are, you can call them as switches that work in a unidirection. So they work when there is a voltage drop of positive negative polarity, considering where the polarity is being applied at. So this is the anode, this is the cathode. So if there's a positive here, negative here, the diode's going to conduct conventional current in this direction. Now, the other mode, so this is the forward bias mode. Now we have something called a reverse bias. In this, we have the same diode. This is anode, this is cathode, but polarity is negative. So this will basically act as a closed switch, unless there's a very high reverse voltage being applied over here. Then yes, sometimes it kind of works, but let's just consider it not to work. Moving over to what a physical bipolar junction or transistor would look like, we basically have this structure like this. We have 3 pins. This one is for an NPN. This one is the emitter, this is the base, and this is the collector. And this is, let's take a very common one, 2N, 2, 2, 2, 2. I believe there's 4 2s at the end. So this is this is how one would look like. It's just like a little black square that you have and 3 pins coming out. The first is E, and then the second is base, and the third is collector. So this is a physical representation of what a BJT is going to look like. Now, moving on, let's discuss about the regions of a NPN. So in an NPN, we have 3 regions. We have an active region. We have a saturation region. We have a region called, what was it? Cutoff. Yes, it was cut off region. So we're basically going to discuss all 3 of these over here, and we're going to see how they all operate, and you're using a graph that's going to tell us. And these are all related to different parts of the NPN that we're going to talk about here. So let's first draw how a NPN will look like when it comes to the general structure. So it's something like this. Over here, we're gonna just draw this. Okay, let me just make it better. Okay, this is how you draw an NPN. So for an NPN, the emitter is going to be facing this way. This is the emitter. It's going to be generally connected to a ground. Over here, we're going to have the base, and the base is going to be connected with a resistor. And usually we have a resistor so that we don't have very high base current, because that kind of messes up, and we keep the base current to be very small to avoid destruction of the whole NPN because it overheats. So this will be connected to a DC supply, positive, negative, and then it's just a DC supply, and let's just say it's connected to the ground here. Now this is the base side, this is the emitter side, and over here on the collector side, we're gonna have a resistor, and then we're gonna have this connected to a power supply as well. But let's just make it like that. This is VS, a source. This is also a source. Let's just call it VB for now. And this is RB, resistor for the base. This is RC, collector side, and this is, you don't have, let's just say there's no resistance here. So this whole section is the collector side, this section is the base side, and this is the emitter side. So this is how we will basically be considering our BJT transistor. So let's talk about the regions that we were talking about. The first one was active region, right? So actually, let's talk about the cutoff first, because it's the easiest to understand, honestly. Where's the razor? There it is. So in the cutoff region, we are basically going to say that the current over here, IB, equals 0. So just think of it not even being here. Now, when IB is 0, the collector current over here is also 0. There is no collector current. Because always remember, in an NPN, the collector current has a good reference to the base current. So no base current means there's going to be no collector current. Now, because there's no current going through RC over here, the voltage, so just consider this connected in this way, like that. So the voltage over here, VS, is also going to be over here, VS over here, which is going to be VCC, which is the collector current voltage. So there is going to be no drop across this resistor, meaning that the voltage is going to be over here is going to be the same as the voltage over here. So this means that across VCE, so here and here, VCE, the voltage is going to be maximum because there's no drop here. The voltage over here is going to be VCC. So over here, the voltage that we're going to get is maximum. So we can say that this whole thing over here is basically an open circuit. Now, so we can easily say that in the cutoff region, the whole circuit behaves as an open circuit. Why? Because there is no voltage drop over here. So the voltage over here is going to be the same as the voltage over here. And we're going to have maximum VCE over here. So it's going to basically behave as an open circuit. So it's going to be like, let's say this positive negative here, connected to the ground, or we're going to connect at the end. And there's a switch here, switches like that. And boom. So it's like an open circuit. Voltage, there's no voltage drop, so the voltage here is going to be maximum. So this is how the cutoff region works. So now we're going to talk about the second region, which is the saturation region. So in a saturation region, we basically keep on increasing the base current, IB, and that causes an increase in the collector current, IC. So this is IB. Increasing this will increase or maximize current over here. But there comes a point where an increase in base current does not increase a collector current, and that point is called the saturation point. So we are discussing about the saturation point. Graphically, if you look at it, it kind of looks like this. So this region till here that I'm going to basically try to color in is the saturation region. So we see over here base current increases to this point, but more increase is not doing any increase in the collector current. So this point is called the saturation point. Now, during the saturation point, let's say this is VS or VCC. So when the current increases, right? The current IC increases, the voltage drop over here increases, right? So the voltage drop over here is going to be high across this resistor. So there's going to be very less voltage appearing over here. So the VCE, that is from this point to this point, VCE is going to be very low, which typically in the case of saturation region turns out to be 0.7 volts. It's around 0.6 to 0.7 volts. It's the same as the operating voltage that we are supposed to see across a diode, which is 0.7 volts in silicon. So during this region, this basically the highlighted thing that I'm going to highlight over here, it basically operates as a short circuit, as a closed switch. So when it's in the saturation region, the transistor basically operates as a closed switch. So that is the second region called the saturation region. So the third region we're going to talk about is called the active region or the linear region. So in the active region, active region is the region where the whole process occurs. So there's like 30 to 60% efficiency during active region, and we see the transistor work as an amplifier or a voltage resistor. So like we were talking about when we were talking about the linear electronics, we were saying something about the voltage regulator in the fans. So why we use transistors in their active region, and we use them as a good source of varying the resistance and having higher efficiencies than linear electronics. So for an active region, for you to understand what an active region is, always remember that there is something called beta, a factor which is constant, multiplying with the base current. So to simplify it for you, how does this work as an amplifier? So increasing the value of beta, which is typically between 20 to 200, but mostly we use it in the range of 80 to 100. We just basically suppose the value of beta, and then we go on with it during our calculations. So using this value of beta, we can say that the collector current has an increase with respect to the base current with a factor of beta. So if let's say that the beta is like 20, then the collector current is going to be 20 times the base current. So this is the active region. So over here, from this point to this point, this line is basically the active region, where we can see that by causing the base current to increase, the collector current seems to increase by a factor of beta. So look, from here, increases, but there comes a point where it saturates, which is fine, so that's why we use it in this region. So the region from here, oh my god, what is wrong with this color? So the region from here to here, this whole region is basically the active region. Let me remove this. Okay, now let's go back to the drawing. Now, to better understand what happens in the active region, let me just explain an example to make it easier. Kind of. Where is this? Yep. This is the emitter. So let's suppose that the beta is 100. We set it as 100, right? And we say that the base current is, let's say, 1 milliamps. Okay? This is the base current. Now, we say that what is the collector current? So using IB and beta, we can say that IC equals 100 milliamps. So you see, we amplified the current from 1 milliamp to 100 milliamp just by varying the base current. So it's an increase, so it's amplifying it. Now, so now you know that in the active region, it works as a voltage resistor or a variable resistor or a amplifier. You can use this formula to find it out. Now, some other formulas that one should know when it comes to transistors are as follows. So the general one is IC equals beta. Why is it not working? IC equals beta IB, right? This is in the active region, and beta is the gain. Then we also have a formula called IE equals IC plus IB. So the emitter current over here, right here, is going to be the sum of the collector current and the base current, just normal electroengineering. So this is what the collector current is going to be. And you can also put the value of IC as beta IB to get the formula IE equals IB times beta plus 1. So this is another formula that you can use. And these are some formulas that you can use, that you should kind of know when it comes to an NPN transistor to like have a better idea of it. And also one more thing, the IE is basically approximately the same as IC, because our base current over here is very small, like we talked about before. So we can just, let's say it's 50 microamps, right? When it's 50 microamps, if you do the calculation, or let's make it easier for you. Let's say the base current is 100 microamps, right? And the gain is 200. Let's say that the beta is 200. So that means that IC is going to be 200 times 100 microamps. Okay, so IC is going to be 20 milliamps, right? Or 20,000 microamps. Now IC is 20 milliamps, and this is 100 microamps. So we can just neglect this part, and we can just say, for easier calculation, that IE is approximately the same as IC. So just to end this all in a quick summary, the transistor can act as a switch, can act as a open circuit, switch as a short circuit, or it can act as a amplifier or voltage resistor, depending on what region it is in. So it's a very great power electronic that we can use in our power systems. So that'll be it for today, and this is just a brief structure of a transistor. So I hope you understood a little, and that'll be it for today. We'll talk something regarding power electronics in the next video. Thank you so much.